Welcome everybody. This is our fifth class in NEET previous year questions for chapter electrostatic potential and capacitance. And this is a subtopic of 12th class chapter electrostatics. In this series before we have made 4 videos and all of those videos are available on our YouTube channel, and name of channel is Point Basics, and there is a dedicated playlist for NEET previous years. Similarly, we have also started for JEE previous years, and those video can also be found on in their dedicated separate playlist. And as usual, if you like these videos and find them useful, then do press the like button, share them as much as possible, and subscribe to our channel. Also, if possible, if you want to donate us something, then you can scan any of these QR codes and in front of your screen and can donate us whatever amount you want. With your help, your donations, we will be keep on making these videos on a regular basis. Now let's start today's video, and hopefully this is going to be last video for this chapter, as we have already covered up to, I think, question number 47. Yes, this we have already covered, and today we will move to question number 48. So let me adjust pen thickness slightly, and here it is. Three capacitors, each of capacitance C and of breakdown voltage V, are joined in series. The capacitance and the breakdown voltage of the combination will be. So we have three capacitance, each of capacitance C, all of these are in series, C, 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 and each have a breakdown voltage V. Now let's leave the breakdown voltage and only talk about the capacitance. Now, as each of them has a capacitance C and all of them are in parallel, so their effective capacitance will be 1 by C plus 1 by C plus 1 by C. So it will be effectively C by 3. So now if we see the options, available options, we have only option A and C, which has capacitance C by 3 as an answer. Now now comes to the breakdown voltage, that what will be the breakdown voltage. Now, as we know that voltage in series is added, so if first capacitor has breakdown voltage V, second also have V, and third also have V, so their combined breakdown voltage will be 3V. So option C will be a valid answer. And now let's move to next question. And suppose if same series, same system was in a parallel combination, in that scenario, suppose this first capacitor, second capacitor, and third capacitor, each of capacitance C and breakdown voltage V, in that scenario, the final capacitance will be 3C and breakdown voltage will remain same as V. Moving to next question. A network of 4 capacitor of capacity C1 is equal to C. This is C. C2 is 2C. C3 is 3C. And C4 is 4C. Conducted to a battery as shown in the figure. The ratio of charges on C2 and C4. So we have to find the ratio of charge, or we can say Q of 2C by Q of 4C. Now let's adjust the question on the screen slightly. And now let's start. So we can see from here, from the diagram, that C3, C2 and C1, all of these are in series. So C3, C2, C1 are in series. It means that they will going to have equal charge. So all of these are in series. It means they all of these will going to have equal charge. The charge on C3 will be equal to charge on C2 will be equal to charge on C1. And how we can find the charge? And that charge this charge is also equal to charge on their combination. What does it mean? Means we have system like this. This is C3, this is C2, and this is C1. Suppose their combined capacitance is C. So if this capacitor has Q charge, then all of these will also have Q charge, and their combination will also going to have the same charge. This is the rule for capacitors. Now we can find their combination, as they are, all of these are in series, so their combination, or once we write it C effective. So C effect, 1 by C effective will be 1 by C plus 1 by 2C plus 1 by 3C, and 3C will be the LCM, 6C. So here we will get 6, here we will get 3, here we will get 2, and C effective will be equal to 6C by 11. So this whole circuit can be reduced into an equivalent circuit where we have a capacitor of capacitance 6C by 11. Then we have C4 here, and we have a battery connected to whole system. So that's how we have reduced the whole circuit into simpler one. Now, as we know, this battery is connected across both of these capacitor, and both of these are in parallel. So both of these potential across both of these capacitors will be same. And if potential is, we know the potential, we know the capacitance, we can find the charge. So we can say charge on 6C by 11 will be, charge on this capacitor will be C times potential. C is capacitance is equal to 6C by 11 into potential, so it will be 6CV by 11. And this is the charge, which is this charge is on effective capacitor, which is combination of C3, C2, C1. So again, as we previously mentioned, that this charge is same as their individual charges. So this charge is also equal to charge of we can say C2. So charge of C2. Now charge on C4. Charge on C4 will be its capacitance, that is 4C, into potential applied across its terminal, that is V. So V, so it is 4CV. Now we have to find the ratio of charge on QCT to QC4. So QC2 divided by QC4. QC2 is equal to charge of Q effective, which is 6C by 11, and here it is 6CV by 11, and charge of QC4 is 4CV. So CV get cancelled. Here we have 3, here we have 2. So it will get 3 by 22 as a ratio. Moving to next question. 3 capacitors, each of capacity 4 microfarad, are to be connected in such a way that effective capacitance is, I think it is 6 microfarad. This can be done. So 3 capacitor we have of 4 microfarad, and we have to make them we can say 6 microfarad. So that can be done like this: 4 microfarad with series in 4 microfarad. Now in combination they will provide effective capacitance of 2 microfarad. And now if we connect a 4 microfarad in parallel, so first this we can say capacitor A, capacitor B, and capacitor C. capacitor A and B are in series, so their effective capacitance will be 2 microfarad, and that 2 microfarad is in parallel with 4 microfarad, so their parallel combination will give 4 plus 2 equal to 6 microfarad capacitance, which is required. So 2 in series with third one in parallel, connecting 2 in series and 1 in parallel. Option C will be the right answer. A capacitor of capacitance C1 is charged up to V volt and then connected to uncharged capacitor C2. Then the final potential difference across the capacitor will be. So we have to find out final potential difference across each capacitor, or we can say we have to find out the common potential. What will be the common potential of these uh, capacitors? So suppose this is C1 and it is charged by potential V. Now, as it is mentioned that it is charged by potential V, and then it is a common assumption that after charging it, battery is disconnected. Because if battery is not disconnected and we connect another capacitor with it, then potential will stay the same, because battery is connected, so potential will not change. And potential can only change if we have disconnected the battery. So as per our assumption, we assume that battery is disconnected after fully charging it. So its charge, we can say Q on capacitor A will be before disconnecting the battery is C1V, because Q is equal to C into V. Now it is connected with uncharged capacitor C2. So this is our C1 and we have connected it with another capacitor C2. Now what will happen? From C1, charge will flow to C2 and redistribution of charge will happen until potential of both of these capacitors becomes equal. So we can say here potential is V dash and here potential is also V dash. So their common potential becomes equal, and after that there will be no charge following and no current will flow in the system. So as now uh, we can say that after battery disconnected, initial charge was this one, and finally what will be our final charge on this capacitor? We will have C1 V dash charge, and on this capacitor we will have C2 V dash charge. So this is Q final, and we know that charge is conserved if battery is disconnected. If battery is connected, then potential remains the same, and if battery is disconnected, total charge, initial and final charge, remains the same. This is our initial charge and this is our final charge. So we can say C1V is equal to C1V dash plus C2V dash, and from this V dash is equal to C1V by C1 plus C2 is equal to V dash. So this is our final potential, and that's satisfied by the option B. So option B will be the right answer. Moving to next question. A 12 picofarad capacitor is connected to 50 volt battery. The electrostatic energy stored in capacitor in nanojoules. So it's a 12 picofarad capacitor, and we can write that total energy stored is equal to half CV square. So half C is 12 into 10 raised to power minus 12, and potential is 50 volts. So half CV square. So we can cut on 6. Now 5 into 6 is 30, into 5 is 150, into 10 raised to power minus 12, and these two zeros, so 100. So this will be 15 into 10 raised to power minus 9, or 15 nanojoule will be the right answer. Option A. Next question. Capacitor of capacitance C equal to 900 picofarad is charged fully by 100 volt battery. as shown in the figure. Then it is disconnected from the battery and connected to another 900 picofarad. The electrostatic energy stored in the system is, so we have to find out total electrostatic energy stored in the B configuration. This is our initial system and this is our final system. We have to find out total energy in the final system. And we have done a similar question where we found out the potential, and here it is, where we found out the final potential. And this can be done in the similar way. This question is also can be done in a similar way, that we can say that initial charge is equal to final charge of the system. Initially, this capacitor C with the capacitance 900 picofarad is charged by 100 volt potential. So its initial charge will be 900 into 10 raised to power minus 12 into potential, because charge Q is equal to CV. So multiply by 100. Now equals to Q final. Now suppose they are because they are connected in parallel. So after connection, there will be redistribution of charge will happen. There will be some current flowing in the circuit for some time, and after some time, potential of both of these capacitor will become equal, and there will be no further current. So suppose that potential is equal to V. So potential of both of these capacitor is V. So charge of first capacitor will be CV and charge of second capacitor is also CV, because potential is equal and capacitance of both of these is also equal. So CV plus CV, so we can say 2CV, and the value of C is again 900 into 10 raised to power minus 12 into potential V. So in this 900 get cancelled and V comes out to be 50 volt. Now we have to find out total energy of B configuration. So total energy, we can find it in two ways. We can find out their individual energy and then sum it up, or we can find out their combination, because both of these are in parallel. So they can be, and both of these have capacitance C, so they can be represented by a single capacitor of capacitance 2C, because they are in parallel. So C plus C 2C, and their potential is V, and V is equal to 50 volts. So both scenario answer will be same. We will be doing with this. So half CV square is the potential energy. C value is 2C. So 2 into C is 900 into 10 raised to power minus 12. And we have 50 into 50. This 2 get cancelled. 25 into 9. So 225 into 100, and these two more zeros. So this is 10 raised to power 4 into 10 raised to power minus 12. So we can write it 225 into 10 raised to power minus 8, and further 2.25 into 10 raised to power minus 8 minus 6, and it matches with option C of our answer options, we can say. Now moving to next question. A parallel plate capacitor has a uniform electric field E in the space between the plates. If the distance between the plates is D and the area of each plate is A, the energy stored in the capacitor is, so we have to find out the energy stored in the capacitor in the form of epsilon node E square and in the form of electric field. So we know basically that energy in a capacitor is given by half CV square. And we have also another formula for energy, that is Q square by 2C. Now we have to convert this energy in the form of electric field, epsilon, area, and these kind of things. So we have to substitute charge here, and we have to substitute C also. Now as we have to include electric field here, so first value of electric field between the plates of a capacitor is given by sigma by epsilon node, and where sigma is areal charge density. So E is equal to Q by A epsilon naught, and from this Q becomes E times A epsilon naught. Now we will use this formula because we have value of charge, and we will directly put this value. So U will become E square A square epsilon naught square divided by twice of capacitance, and capacitance is equal to epsilon naught A by D, and D will go on the top. So A square get cancelled and epsilon square get cancelled. So we will be left with half epsilon naught E square into A times T, and that is option C is the right answer. Moving to next question. So two identical capacitor, both capacitors are identical, of equal capacitance are connected and shows in the circuit. Terminals A and B are the key connected to charge the capacitor C1 using the battery of EMF V volt. Now disconnected A and B, the terminal B and C are connected. Due to this, what will be the percentage loss of energy? Now, as per statement that C1 and C2 are equal, so let us assume that their value is equal to C. So this is C and this is also C, and we have to find out the percentage loss of energy. So what we will do, we will find initial energy and final energy, and then we will compare both of these. So initially our system is like this, that this capacitance is connected to a battery, and suppose it is connected for some good amount of time so that it is properly charged, and after that it is disconnected and connected to a second capacitor, second identical capacitor. So here we will use two things, first energy and second charge conservation. Because battery is disconnected, so charge will remain conserved. So initial energy will be half C V square, and initial charge will be C into V. Now suppose their final final potential is V dash. When we have disconnected A and B and have connected B and C. When we connect B and C, there will be charge redistribution will take place, some current will flow, and there will be some final potential, after which system will goes to equilibrium, and there will be no further charge flow or current flow. And suppose that potential is V dash. Now in that scenario, final charge will be due to this capacitance plus this capacitance. So due to this capacitor, our charge will be CV dash, and due to this again CV dash. So CV dash plus CV dash is equal to 2CV dash, and Q initial and final should be equal as charge is conserved. So CV is equal to 2CV dash. C get cancelled, and from this V dash comes out to be V by 2. So now coming to final energy, this capacitor will have energy and this capacitor will have energy. So our final energy will be sum of them. So half C V dash is equal to V by 2. So V by 2 whole square. So V square by 4. This is energy due to this capacitor plus energy due to this capacitor, as both of these are identical. So again energy will be same, half C V square by 4. So this will be CV square by 8 plus CV square by 8. We will get CV square by 4 as a combined. So our initial energy is CV square by 2 and final energy is CV square by 4. What we can say, that loss of energy, delta U. Loss, if we are calculating loss, then it's initial minus final. So U initial minus U final, it will be CV square by 2 minus CV square by 4. Solving this, we will get CV square by 4. And in percentage, it will be delta U by U initial. So CV square by 4 divided by CV square by 2. CV square get cancelled. This 2 on the top and 4 in the denominator. So it will be 2 by 4 or half or 0.5. And in percentage, it will be 50% is the right answer. Moving to next question. A capacitor is charged by a battery, the battery is removed and another identical uncharged capacitor is connected in parallel. The total electrostatic energy of the resulting system. And we just solved it, that this is the same statement, that there are two identical capacitors, one of them is charged and then disconnected from the battery and then connected in parallel with the second uncharged capacitor. This is the same status, the same scenario. Here energy reduces to 50% or 1 by half. Energy becomes 1 by half. So energy decreases by a factor of 2. Option B will be the right answer. Next question. So now have a slightly different statement, and again we have to again calculate that amount of energy dissipated. Here we have values of capacitance as different, here 2 microfarad and here 8 microfarad. In previous question these were equal, so in this our values will slightly change. So again, suppose our initial energy U initial will be, because initially this 2 microfarad capacitor is charged and we are ignoring here micro, so it will be half C, that is 2 into potential, that is V square. So our initial energy is equal to V square and our initial charge will be C into V, so 2 into V our initial charge. Why we are ignoring micro? Because we have to do only percentage calculation, so we will divide one thing by another thing and micro will also will be both of these and it will get cancelled. So that's why we are ignoring the micro 10 raised to power minus 6 here, for so that our calculation can become easier one. Now going to final scenario. Suppose after connecting this terminal and disconnecting this, our final potential is V dash. So our final charge will be 2 into V dash plus 8 into V dash, because Q is equal to CV and both of these should be equal. So 2V is equal to 10, 8, 2 plus 8, 10, 10 V dash, and from this V dash comes out to be 2V by 10 or V by 5. Now our final energy U final will be half 2 into potential square, that is potential is V dash, so V square by 25 plus for 8 microfarad, there will be half into 8 into potential is same V by 5, so V square by 25. So this is 1 and this is 4. We can take V square by 25 common and it will be 1 plus 4, 5, and V square by 5 is the final value or final energy. So percentage of store energy dissipated. So we have to again find the loss. Dissipated means we have to find the loss. So loss will be initial minus final. So V square minus V square by 5, or it will be equal to 4V square by 5. In percentage it will be delta U by U initial. So 4V square by 5 divided by initial energy, that is V square, we will get 4 by 5, that is 0.8, or in percentage terms it is 80%. Moving to next question. A parallel plate capacitor of capacitance C is connected to a cell of EMF V and then disconnected from it. So again we can say we charge it to up to value Q and then it is disconnected, so value of charge will remain constant. A dielectric slab of dielectric constant K, which can be just fill the air gap of the capacitor, is now inserted in it. So which statement is incorrect? So first we charge the capacitor by potential V, so its charge becomes Q is equal to CV, and as now it is disconnected from the battery, so charge will remain constant or charge is conserved. And if you see the statement D, the charge on the capacitor is not conserved. This statement is the wrong statement. So this will be the answer, option D, as we have to find that which statement is wrong. Now let's also analyze the other three options. So potential energy, potential difference between the plates decreases k times. Now as dielectric slab of dielectric constant k is introduced, so new capacitance C dash becomes to be k times C. Now as charge is constant, so CV, or we can say Q initial, should be Q final. Q initial is equal to CV and Q final is new C times new potential. New C is Kc and new potential suppose V dash. So here C get cancelled, V is as it is, and V dash comes out to be V by K. And as K is greater than 1, so new potential is decreased K times. So option A is the right one. Now the regarding energy stored decreases k times. So energy is can be represented by q square by 2c. As charge is conserved, only capacitance changes. So our final energy or new energy will be q square 2kc. So it will be old energy, or we can say initial energy time divided by k. So our new energy decreases. So again decreases k times. And change in energy will be, so we have to find change in energy. Change in energy we can find easily. Delta U will be U final minus U initial. So it will be we can say Q square by 2 Kc minus Q square by 2C, and we can take Q square by 2C common. Q square by 2C common, it comes out to be 1 by K minus 1, and value of Q is equal to CV. So it will become C square V square by 2C, 1 by K minus 1. C get cancelled, so we will be left with half CV square 1 by K minus 1. So again change in energy is also right. So option D is the wrong option, which we have to find out. Moving to next question. Percent the energy required to charge a parallel plate condenser or capacitor of plate separation D and plate area A such that uniform electric field between the plate is E. So again we have just previously solved this question, where we found out that energy stored in a capacitor is equal to half epsilon naught E square into AD. This is the energy stored in the capacitor. It does not mean that a battery has to provide this amount of energy. Battery might have to provide an energy greater than this, which is the actual case, that in reality the amount of energy provided by the battery, some of out of which is lost in the form of heat as current flow through the wires or the plates, and only some part of it or some fraction of it is stored in the capacitor. So let's find out that how much will be the energy provided by the battery. So we know that power is equal to VI. This is the power of a battery, that if you have suppose 5-volt battery or 3-volt battery, this is the power provided battery, and energy provided will be power times time. So it will be VI into T. And now we know that it is current times current into time, and we know that current's definition is current is given by rate of change of charge with respect to time. So we can say dq is equal to I dt, or q is equal to I into t. So current into time is equal to charge, and these all calculation we are doing for battery, not for the capacitor. For battery, its power is its potential difference, its terminal potential difference, and the maximum current which it can provide with that potential difference. And energy provided, it will be power into time, and power is Vi into time. So I into T is equal to charge, so it will becomes V into Q, or Q into V. So now we know that for as we are charging here capacitor, and for capacitor charge is given by CV, because charge is conserved. Energy might not be directly transferred from the battery to the capacitor, as it is somewhat lost in the form of heat, but charge is conserved. The amount of charge transferred from the battery is equal to amount of charge is collected on the plates of capacitor. So Q is equal to CV holds for both battery and the capacitor. So here energy will become V into CV, so CV square. And you can easily see that it is double of the energy stored in the capacitor. And now energy stored in the capacitor is either half CV square or Q square by 2C, or this formula which we recently discovered in our some previous question. So it will be just double of it, that, and here answer is given in the form of this. So it will be again double of this, and double of this is epsilon naught E square AD. Option C is the right answer. Next question. Two condenser, one of capacity C, other of capacity C by 2 are connected to V volt battery. The work done in charging fully both condenser is, so we have to find out that work done in charging fully both of these. So work done will be just the amount of energy stored in both of these. So in first capacitor, potential difference across its terminal is V. So in first capacitor, half CV will be stored, plus in second capacitor, half C by 2 into V square will be stored. So we can take half CV square common from both of these. Here we will be left with 1, and here we will be left with half. So 3 by 2. So it will be 3 by 4 into CV square is the total amount of work done that needs to be done in charging both of these in ideal conditions. So option B will be the right answer. Next question. So capacitor is charged by connecting battery across its plate. It stores energy U. Now the battery is disconnected and another identical capacitor is connected across it. Then energy stored by the both of capacitor or the system will be, and we know answer is U by 2 because both of these are identical, and we have already solved a question like this. I think it was question number 56, 55 or something. Yes, this was the question where energy lost was half, so remaining energy is also half. So in case of parallel capacitors, when we charge one and then connect it to with another, the energy we can say energy loss is half, and energy left is also half. So U by 2. Now moving to last question. If the potential of a capacitor having 6 microfarad is increased from 10 to 20 volt, increase in its energy. So we can say final energy will be half C into 20 square, and initial energy will be half C into 10 square. So increase in energy delta U will be U final minus U initial. So half C will be common, and value of C is 6 microfarad. So 6 into 10 raised to power minus 6. 20 square minus 10 square, that is 400 minus 100. This is 3. So 3 into 10 raised to power minus 6 into 300, that comes out to be 9 into 10 raised to power minus 4 joule. Option C is the right answer. So with this, our this chapter is finished, and hopefully again whatever we have covered here is helpful for you in somehow. If you have any doubts, suggestion and comments, you can put them in comment section. I will try to implement them or solve them. And if you like this video, do like the channel, share like video, also share the video and subscribe to our channel. And if possible, do make some donations by scanning these QR codes. Yours, even a small amount of donation help us a lot, and also motivate us a lot to keep this series ongoing and keep on making in these videos on regular basis. So with this, again, thanks for watching, and we will meet in next video.